All right, everybody, welcome back to CS 125. It's a beautiful spring day here in Champaign. I hope you guys are well, wherever you are, and ready for some more computer science. So we have one more week left together. That does not mean that what we're doing today and through the rest of the week isn't tremendously important or interesting. It is. On some level, because of how we set up CS 125 and because of the fact that it occurs so early in the program, some of the most important material we cover in the entire semester is now. This is the stuff that's going to really put you in a great place to continue on with 173, with 225, and with other courses in the future, right? We sort of built you up to this point all semester, bit by bit. And then finally, kind of at the end of the semester, we can talk about some really cool things. And so this week's homework problems, today's class are really going to be focused on that. I'm joined today by this little furry creature who apparently is going to help. Are you going to help teach? No? You look at the screen. She likes to sit on my laptop. It's warm. All right, so today what we're going to do is we're going to talk about the second data structure that you meet in heaven, which is known as a map. We've talked about lists. You guys have implemented lists several different ways and looked at some of the trade-offs. And we're going to do something similar with maps. Maps turn out to be something that we don't need to be afraid of. We can actually build one. You guys will do little pieces of that on the homework problems. And just like we did with lists, we can talk about some of the trade-offs with different map implementations. But the first thing we have to do to get to maps is to talk about this mysterious and extremely interesting function that we can use that turns out to have lots of uses all over the place. And so let's start there. So this is not a course on theory, and really what we're introducing hash functions for is to get us to the point where we can implement maps. But it turns out that if I had to put in a bucket just a couple of things that are tremendously useful about computer science that turned out to come up all over the place, that are just from a programmer perspective, like a useful thing to know that the universe is capable of, I would put hashing and hash functions in that bucket. Because not only do they get used for maps, but they get used lots of different places. And actually, once you start to recognize them, you'll see them all over. So here's what a hash function is for our purposes, at least getting started. Now, we're just going to posit the existence of this function. We're not going to talk about why they exist. We're not going to talk about how they're implemented, which is pretty nasty. We're just going to point out that if we had a function that had these following properties, here's some of the things that we could do with it. Okay, so what are the properties that we need from this function? First of all, the function has to be deterministic. So when I give it the same input, it should produce the same output. That's determinism. So if I take a hash function and I apply it to the same object twice, I should get the same result. Okay? So the second feature I want is uniformity over the space of outputs. So a hash function returns some value, and the hash functions that we're going to be looking at typically return numeric values. What we want is if we take a bunch of different inputs, we want to have uniform output, meaning that it's sort of, the outputs are evenly distributed over the output space. So if my hash function returns an integer, sometimes I want to get really small integers, sometimes I want to get really big integers. I want it to be, if I took a bunch of different objects and hashed all of them, and computed this hash function, a bunch of different inputs, and computed the hash function on all of them, I want to get outputs that kind of are uniformly distributed over the space of outputs. And finally, and this is only important at the beginning, and we'll relax this assumption later when we talk a little bit about cryptographic hash functions, but at least at the beginning, I want something that's easy to compute. This has to be efficient. So given an input, it's supposed to be fast. Okay? So it turns out that categories of functions with these properties exist. They're frequently known as hash functions. And I taught this topic for a long time before I thought a little bit about some of the etymology behind this, right? So like hash, right? I'm not exactly sure where the idea of a hash function comes from. But some of you, particularly people who grew up in particular parts of the United States or have been to particular types of dining establishments or had gone before all this crazy stuff happened, might know what a hash is, right? Hash is a dish that consists of essentially a lot of ingredients that have all been chopped up into very fine pieces or kind of mixed together. That's what a hash is. And to some degree, a hash function is designed to do that. So it's designed to take lots and lots of pieces of the inputs and kind of mix them up together to get one output. The values that are returned by functions that have this property sometimes are known as a hash, sometimes known as hash values, hash codes, digests, or simply we call it the hash of a particular input. now that we've posited the existence of such a hash function, and it turns out that the existence of these functions and some of the properties that we think they might have actually have some pretty interesting connections with theoretical computer science that we'll return to at some point and just comment on briefly. But let's treat this as something that we do have, because that's true, and think about what we could do with such a function. Where would it come in useful? What would be some of the potential use cases for this type of feature? Now, again, it may not seem obvious at first, but it turns out that hashing and hash functions get used all over the place, right? So let me set up this following scenario for you. So you're downloading some big file from the internet. And this is one of these things that used to be a little bit more of a concern for normal people back when the internet was a little slower. Now, most of the things that we download on a normal basis download pretty quickly, even if they're pretty big files. But of course, that depends on what the internet is like where you are. That may not be true. So imagine the following scenario. I need to download some big piece of software. Let's say this is like some installer that I'm going to use to install a big program like Adobe Photoshop or something like that. Now, it's possible, not likely, but possible, that along the way, from wherever this file was on the internet to my machine, some portion of it gets corrupted. So along the way, some tiny piece of that data gets mishandled, and as a result, I end up with a file that's not exactly the same as the original file. Now, it might turn out that it just ends up being corrupt and it won't run, but that change might cause the installer to break or misbehave in a way that might be damaging for my computer, right? So essentially what I want to be able to do is verify that the file that I received is the actual file that was sent, or the file that the person who posted this file wanted me to get, all right? And I want to do that sort of before I install, right? So essentially I download the file, and I have this file on my computer, but I'm not exactly 100% sure that it's the right file. So I want to verify. How do we do this? So if I don't have a hash function, my options here are pretty limited, right? Essentially one option is download the entire file and then download it again. And if it took a long time to download it the first time, then it's going to take twice as long to implement this particular approach. And now I have two copies of the file, and the idea is that I compare them with each other to make sure they're the same. And the assumption here is that any problems that I might have along the way are ephemeral, right? So if I have a small piece of the data that gets corrupted the first time, it won't get corrupted the second time. Now, this approach doesn't work if, let's say that I downloaded the file from some website, but it turns out that the website's copy was corrupted. So even if I download it twice, I get two copies of the same corrupted file. So this doesn't handle certain types of errors either. And it's also slow, right? Okay, but keep in mind, we have this new tool in our toolbox known as the hash function. And the hash function has these properties. So first of all, it's deterministic. So the idea is if you and I have the same file and we run the hash function over the contents of that file, we should get the same answer. The second is it's uniform, and this turns out to not be important for this application, but it's important for other applications. And the second one is that it's efficient to compute. Actually, the uniform turns out to be important too with regards to what are called collisions, which we'll come and talk about in a little bit. The last thing is that this is efficient to compute. So once I've downloaded the file, it doesn't take me long to run this hash function on the contents of the file and get the answer. And so instead of downloading the file twice, if I have access to a hash function, I now have another option, which is that I download the file, then I compute the hash function. So I take the contents of the file and I feed them into this as the input into this hash function, which then spits out an output. Then I compare that hash, which is small, much smaller than the file. So hash functions typically produce small outputs, like a single integer, or sometimes maybe like a 128-bit integer or 256-bit integer, right? That might seem like a big number, and it is a big single number, but it's much, much, much smaller than a 120 gigabyte file that has lots and lots and lots of data. So what I do is I download the file, I compute the hash on the file that I downloaded, and then I compare it with the hash that the person who posted the file provides to make sure they're the same. Okay? And this turns out to be something that's actually done in the wild, right? So here's an example And you'll see that this is a package that installs a document formatting program called LaTeX on your computer. It's a fairly big file. You can see here that it's about 4 gigabytes. And the people that posted this file have posted several different hashes for the file. I kind of wish that I had downloaded this so that I could do a demo for you guys and you guys could see that this actually works. I haven't downloaded it. But these values here, so this is a number in what's called hexadecimal notation, where I have not just the normal 0 through 9, I also include A, B, C, D, E, and F, which allows me to represent 16 distinct values. I have another hash value here. These are different types of hash functions. So this is a hash function called MD5. This is the value if I compute the hash using a hash function called SHA-256. And then this even larger value here is the value if I compute the hash using a hash algorithm called SHA-512. As maybe you've guessed, the 256 and 512 in the name corresponds to how many bits of output the hash function produces. So SHA-256 produces a hash value that has 256 bits of output. SHA-512 produces a hash value that has 512 bits of output. And you can see that's why the hash value for 512 is roughly twice. Is roughly twice the length of the hash value for SHA-256. So the idea here is that if I was downloading this file to my computer, I would download the file, I would wait till it finished, and then I would run a hash function on my machine on the copy of the file that would produce a value, and then I would compare the value with the ones that are posted here to make sure that my copy is the same as the copy that was posted. Okay, so and again, you can see that this is an example with MD5, right? Now this is an old version of this file. It's changed since then, right? So actually you can see that the new file that is posted now in 2020 has a different hash value than the old one that was posted around the time that I originally wrote these slides, right? So, essentially, let me get this to move forward for me, right? So if I'm using MD5 and I'm expecting a hash value of this is what used to be posted on their website, I run this command on my computer. This is 2017 version of this particular package, and it produces this output. And what that guarantees to me, or doesn't guarantee, but with a very, very high probability, I have the right copy of the file. Okay. So, and again, here's another use for this, right? So, imagine that you sent me a copy of some Microsoft document, which I didn't open because I don't like to open those types of documents. But anyway, so let's say that at some point later, you have made some changes and you have a local copy, but you can't remember if I have the most up-to-date copy of that document or not. And this happens all over the place. In fact, the Git version control system that you guys are using, one of the things that it has to think about is this type of thing, which is, is the copy, and when you guys start collaborating with your partner for the final project, you'll notice this, one of the things that Git does for you is it determines if the remote copy of your work has new contents that you don't have locally. And when you do a git pull, if that's the case, it'll fetch those contents and update your working copy. So again, we know without a hash function, our options here are pretty limited, right? You could send me the file again, but remember, just to make sure that I have the most up-to-date copy, but remember, I have this hash function with these cool properties, right? And so the idea is that the hash function, the hash value, serves as a fingerprint of the contents of the file at a particular point in time. So if you take the hash of a file and you make some changes and then you take the hash of the same file again, you're going to get two very different values. And actually, it's this second property called uniformity that makes this, that helps us with this particular property. So one of the properties of a good hash function, particularly the type of what are called cryptographic hash functions that some of these examples are using, which we'll talk about a little bit later, is that even if I make a tiny, tiny little change to the contents of a file, the hash value changes by an enormous amount, right? So essentially, if I add like one character to my document and then rerun the hash function, I expect to get a very, very different value. The value is not just slightly different, it's completely different. It's like an entirely new random value. But if I run the same hash function on the same contents twice, I get the same hash. So, again, once I have a hash, it allows for easy comparisons of the contents of two files without actually having to compare the entire contents of the two files. So if you have a file and I have a file and we're trying to figure out if they're identical, if we compute the hash functions and compare the hash values, that's sufficient to compute whether or not the files have identical contents. Now, this is essentially the basis for the Git version control system. Now, I'm not actually sure if this is up to date in the sense that I don't know which hash function Git is currently using. It may be using a different hash function. But, if you guys have gone, and I'll just, go to a random, let's see here. I'll go to a random GitHub repository. Here's a project I'm working on with some of my core staff, right? So if I go to this commit, if you look over here, right, what is this value? Let me make sure that you guys can see this. Oh yeah, this is a hash value, right? That's the way that Git identifies everything. Files, hashes, etc. So every time you commit, what you're doing is you're essentially causing Git to create a new snapshot of your files, all the files in your project at that point in time. The way that Git identifies those snapshots is through hash values. It's also the way that Git identifies file contents. So you might have noticed if you take, let's say you've committed all your changes, you make a small change to a file, you go to commit, it will bring up the commit dialog. If you undo that change and go to commit, it'll say there are no changes to the files in your project. The way that Git knows that is it's computing the hashes of the files. So it computes the hash of the file you're working on, and it knows what the last version of the committed file was, what its hash was, and if the two are different, then the file is dirty, and those changes can be committed. If they're the same, the file is identical, and there's no new contents to commit. All right. So, and again, when you push to github.com, just to sort of drive home how useful and interesting these hash functions and their outputs are, right? More or less what happens is that when you do a push, your copy of Git says to this GitHub server, hey, I've got my copy of the repository has the following content, and it sends along a bunch of hash values. And the server compares with what it has, so the server also has a copy of your repository. And if the server contents are the same as your local contents, then nothing happens. There's no new information that your computer has that it needs to upload to github.com. If the contents are different, then that's the point at which the push starts to actually transfer some information. So again, the entire Git version control system is really heavily built on top of hashes, right? Hashes for file contents, hashes for commits, everything, basically every object that Git works with, and you can think of it that way. Internally, Git is a system, and it represents various entities that it manages as part of versioning the contents of your repository as objects. Every object is identified by hash. Okay, now let's talk about when things can go wrong, because what we've been speaking about here is this ideal world, and part of the idea is that if I take a file and I compute the hash value, that should uniquely identify the contents of the file. Okay, now you might wonder, is this actually possible to do? It seems counterintuitive, right? And it's actually a really interesting thing to wrap your mind around. This idea that, because the hash values are small, right? So think about it. Let's say I use even a pretty big hash function, a hash function that produces a pretty big output, like SHA-512. That produces a 512-bit hash value, okay? But again, we're talking about, let's say you downloaded a movie off the internet. Obviously, nobody would ever do that because it's not legal, but let's say you did, and you computed a hash value. You're saying that I can summarize the contents of this huge file that might be gigabytes and gigabytes with a single value that's only 512 bits. And my answer is, yes, you can. And it turns out that systems like Git are entirely predicated on there never being any collisions between a hash. So what we mean by a collision is if there are two different inputs that produce the same hash value. Now, some hash functions or some systems that use hashing expect there to be lots of collisions. When we talk about maps, we're going to build our maps in a way that allows us to gracefully handle hash collisions. Okay? But this is typically a problem when the size of the hash is small. So if your hash, let's say your hash value is only one of only between 0 and 256, right? Or 0 and 255, 256 values, right? Then if you hash 512 documents, you're going to expect to get a bunch of collisions, right? Because some of those documents have to end up at the same hash value. It's sort of like, you can think about a hash function as like selecting one item from like a bunch of different, putting like one ball into a bunch of different containers, right? Each container is a hash value. So if my hash function only has 256 outputs, then eventually if you give me enough balls to put in there, right, there are going to be 2 that are going to end up in the same place, right? 2 of them in the same slot. Now, again, once I make the size of the hash large enough, it turns out that the size of the hash does not need to be that big before the probability of collisions is infinitesimal. It's just tiny, tiny, tiny. And so essentially we kind of plan for it never to happen. So if Git, for example, if this would ever happen to Git, its world would just explode, right? I mean, Git is entirely predicated on this idea that this will never ever happen in practice. And actually, again, that says something a little bit interesting about humans and how we store information, right? This idea that if you took probably every file on Earth, every single file, no matter what the contents are, and you computed the hash value using a hash function that has a reasonably large output, you would never get the same value. And so even though we humans create these massive files, the amount of actual entropy in the world, the amount of different content we're creating is actually pretty small, right? Okay, however, with the small hash function, it turns out that collisions happen a lot often than we think. And this is related to this fun piece of math that's known as the birthday paradox. And some of you may have heard of this already, and if you haven't, it's a good thing to know because it comes up on interviews and it's one of these things that, just turns out to be more counterintuitive than you might think for some of you. So here's the question. If you have a room with 100 students in it, what is the probability that 2 will have the same birthday? So if we were together in Lincoln Hall, I would say, okay, there's 400 people here. Obviously the probability at that point is pretty high because there's only 356 days in the year, 365 days in the year, sorry. But let's say that's 100 students, okay? So again, there's 365 days in the year, so 100 students. So you might think, well, is it like a third or something like that? Maybe it's a little higher because maybe whatever. It turns out to be like almost 1, almost certain that you are going to have 2 people with the same birthday in a room with 100 students. The other fun way to ask this question is to say, let's say that we want there to be a 50% probability. So how many students do we need in a group before there's a 50% chance that 2 of them have the same birthday? So if I have one group with this many students and another group with this many students, it's a pretty good chance that one of them, right, will have 2 students with the same birthday. It turns out only 23. So your lab section, right, that you guys used to attend back when the world was more normal, had about 40 students in it. So it was pretty likely that 2 of the students in your lab section would have had the same birthday. So you might be wondering, why did we just suddenly stop and talk about this random little piece of mathematics? And the reason is, it turns out that this is related to our hash functions, because this result means that hash collisions are more likely than we might think. Okay, so let's relate this back to hashing. So we call this the birthday hashing paradox. So how many documents do I have to hash before I find 2 with the same hash with the 50% probability? Now, this turns out to be very dependent on the output size. So you might think that this is a very similar setup to the previous problem, but here's the difference. In the previous problem, we're talking about birthdays. That's days of the year. There are only 365 days in the year. Okay, so that doesn't change. What changes is the size of the group. Here, what I'm saying is I'm fixing the probability, and I'm asking how many documents do I have to hash. But there's this important part of the problem that I have not fixed, that I had to fix before, which is how large is the output of my hash function. So with the birthday, it was sort of like I'm using a hash function that only has 365 different outputs. With our hash function here, we can choose how large the output size is. So let's say that we have 16 bits. Okay, so remember, going back to our earlier example from that that big 4 gigabyte MacTech package that we found online. That had MD5 hashes, and then it had a SHA-256 and a SHA-512. Okay, so in the wild, we see hash functions that use like that many bits, right? When we need to do unique fingerprinting of document content. But let's say that we use a 16-bit hash function. So this hash function produces 2 to the 16 different outputs. Okay. In this case, I can only hash 300 files before there's a 50% chance of a collision. You know, even a small piece of Android, a small Android project easily has like 300 files in it, right? I think I looked at this last semester, and you know, the starter code that we gave you for the machine project had, I think, over 300 files in it already. Okay. What about 32 bits? So this is the size of an integer in Java, right? Integers in Java are 32 bits, so they store from 2 billion to negative 2 billion, 4 billion different values. But even if my hash function will output 4 billion different values, once I've hashed 77,000 files, there's a 50% chance of a collision. This is also assuming the hash function is uniform. And we talked about that as an important property before, meaning that when I hash a different input, each of the outputs is equally likely. Okay, let's try to make some bigger hashes. So what about a 64-bit hash function, right? Now I can hash 5 billion files before I have a 50% probability of a collision. GitHub.com at the time I checked had 1 billion files. That's probably even much larger now. Okay. So once we start to get to even more large hash functions, now we're starting to get to the place where we start to feel more comfortable. So for example, if I use a 128-bit hash function, I don't even know what the name of the denomination for this number is, but it's like big. Right? That seems like a large number. Now, again, keep in mind, we really need to drive this probability down to like almost 0. It's not okay for 50%. 50%, Git is not okay with 50%. Git will just fall over and die with 50%. We need 0.000001, maybe, right? So at the time that this was written, Git was using a 160-bit hash function. But if you imagine going up to 256 or 512, right? 512 bits. So now I can hash a number of files that's roughly on the same order of the number of atoms in the universe. That's probably enough, right? And so, you know, the trade-off here, you might ask, well, why not use a larger hash function all the time? Is that storing the outputs from a hash function that produces a larger output takes up more space on your computer, more space on your hard drive, and more space in memory when certain programs are running. So, you know, we want to choose a hash function that produces a large output value, but we also don't want to choose one that's so big that it's going to cause the program to consume more of disk space and more memory than we might want. Okay, so again, this is, you know, this trade-off between sizing our hash function. We choose small values, we end up with a pretty high probability of collisions, but it's possible to choose a reasonably sized value for our hash function output that makes the probability of collisions almost infinitesimal. Okay, so far, hopefully I've convinced you that there are some useful features associated with hash functions. But we're just getting warmed up here. We have a lot more fun stuff to do. And it turns out the next bit of this, right? So up until now, it's kind of like, oh, this was interesting, but what does this have to do with Java or programming? Remember object? Remember capital O object? All those, you know, what feels like years ago when we were talking about object-oriented programming? Remember, we pointed out that it had a couple, every object in Java has a couple of these common methods. One was toString. We used that in debugging, and we talked about why that's useful. Another one was equals. You guys have implemented that. We've talked about why that's useful. Hash code. We brought that up. We were like, oh, we'll get back to that way later. Well, here we are. Okay. So what do I do with hash code? So you remember arrays? Remember arrays like from back in February? You guys are still using them from time to time. Tremendously useful data structure. This was our first example of the sequential data structure. Arrays put items in order. And on some level, when we talked about arrays, we talked about the fact that arrays are a data structure. They take the raw data values that are contained within the array and they bring structure to them. They put them into an order. As part of doing that, they associate metadata, like other data structures, with each data value. So these data values 5, 6, and 7 are now put in an order where 5 is first, 6 is next, 7 is last. And in the process of doing that, one of the things I've done is I've associated a new piece of data, metadata, with each of my original data values. So 5 now is at index 0, 6 is at index 1, and 7 is at index 2, right? Arrays work great, and we have used them with great success to do a variety of different things, but they have this problem, which is that I can put anything into the array, but so the values in my array can be of any type in Java. You can make arrays of any Java object and all of the primitive types. However, the indices, right? So that piece of metadata were always integers. Okay? Arrays put things in order, and that kind of, on some level, that sort of makes sense, right? In the sense that when I put something in order, the piece of metadata that I associate with it is an integer. It indicates its position within the ordered items. However, we can relax this restriction, right? And we can create a new data structure, and this goes along with arrays and lists as one of probably the two most powerful data structures that you'll use as a programmer. And this is something that's known as a map. Okay, map is a little bit of a complex term, right? So I just want to be careful with it in the sense that a lot of times when you think about maps, when you guys have used maps within your MP, for example, you've been thinking about maps of physical space, right? A map that allows you to navigate across the country or whatever. Where that's different than the data structure map. Sometimes it's known as a dictionary, or sometimes it's an anonymous object, right? A map allows us to essentially use any object type like an array index. And so if you think about an array as establishing a mapping between indices that have to be sequential and values, a map allows us to establish mappings between any key and any value, where the key and the value can be any Java type. So when we talk about a map, what we're really doing is the map is storing mappings. Each mapping maps a key to a value, and the map allows us to both set and then later look up these mappings based on a key and retrieve the value that we store for. Okay? So here's an example. A map like list is both an interface, and then there are different implementations of it. The implementation that we're going to be using for some of these examples is called a hash map. And that might give you a little bit of a clue about why we just talked about hashing and kind of where we're going with this, right? Because it turns out that one of the ways to implement this map data structure in Java is to use hashes and to use the hash code feature that all Java objects provide. But for now, let's just sort of look at this together. This is where we're declaring a map. Now, just like lists that we saw, maps are a data structure that's parameterized by type. So when I create a map, I need to tell Java which type of value it maps from and which type of value it maps to. So remember, when I used a list, I only provided one type inside these angle brackets. That's because a list when I create a list, I only care about the type of object that I put in it. The indices are always integers. With a map, I get to specify the type of both the key and the value. So this map is going to map from strings to integers. It allows me to store mappings from strings to integers. I can put this is putting a new mapping into my map. So put adds a mapping to the map. This adds a mapping from test to the integer value 5. Once I've added a mapping to my map, I can then retrieve the value for that key. So once I've done put test5, if I do get test, this is a string, this is going to retrieve the integer value 5. Maps store mappings from keys to values. If I overwrite the mapping for a particular key, I associate a new value with that and I overwrite the old value. So here what I've done is I originally established a mapping from test to 5. Now down here, I'm going to modify that to map from the string test to the value 7. And then when I get that mapping, it's going to bring back 7. We'll have a chance to work with these in a playground in just a minute. And again, maps are another one of these tremendously useful data structures. And if you don't believe me, just observe that they exist in pretty much every single programming language. And in a lot of programming languages, they are just built right in. They come for free. In Java, we have to like import them from this map class and stuff like that. But in Python and in JavaScript and a bunch of other languages, you just start using them right off the bat. So in Python, we refer to these as dictionaries. That's the Python term for them, but they essentially behave exactly the same way. In JavaScript, I call them anonymous objects. Now, one of the things you'll notice is that in both of these other languages, I have a syntax for working with maps that allows them to look very, very, very like an array. So remember we had array syntax, we used a bracket notation, we put an integer in there, and we were able to set and retrieve values from the array. I can't do this in Java. It doesn't allow me to work with maps in such an elegant way. There are languages that have succeeded Java that allow me to do that, such as Kotlin, but in Java I have to use this put and get explicitly on an instance of the map. But in Python and JavaScript, I can just work with them in this very, very elegant formulation by just treating them as almost like they're, the syntax makes them look very much like an array, except over here, instead of an integer being put inside the square brackets, I have a string, any type of object. C++ has something called a map, Go calls them maps, Perl had something called maps. Perl is a hopefully largely dead programming language that people used to use for Python type projects. And you know, when maps end up in this space where they kind of blur a couple of different data structures together. So this is called the maps, and you call what you put into mappings. Sometimes people call them key value stores because you associate a value for each key in the map. You'll hear different terminology here, but this is a very, very, very common data structure. All right, so let's have some fun with maps, right? Just kind of play around with them and get a sense of what we can do with this data structure. Okay, so first thing I'm going to do now, like I suggested, I'm going to suggest that we add type parameters to our map. If I don't do this, here's what's going to happen. So let's say I do map example.put. So I'm going to establish a mapping from test to me, and then I'm going to do string s is equal to map example.get test. What you're going to see is the same problem I had with lists, which is that if I don't provide those type parameters, I can put anything I want into my map, but everything I get out of it is an object. Everything gets upcast to object. So instead, what I'm going to do is I'm going to say this map maps from strings to strings. And again, you get to choose any type you want here to put into your Java map. Okay, so I'm going to add these over here on the right side, and now this works fine, right? And I can do things like submit out to println, because Java knows that this is a string. I can print the length, and I'm good, right? So now let's make this a little bit nicer to show how we can retrieve values from the map. Okay, so I created my map. I'm going to pull some, oh, I forgot to put a value in. Okay, so I'm going to load a value into the map. Oh, sorry. I still need to put the value in. Okay, so I'm going to do map example put test, and I'm going to put me. However, you did notice something, which is that in Java, if I tried to retrieve a value from a map and that key doesn't exist in the map, I get null, right? So here I'm going to get null because I haven't added a mapping for that key yet. If I add a mapping for that key, let's put a mapping for capital test, and we'll put it to deuces, since she's still here hanging out with me. Now I see that this works, right? So like I mentioned before, if I reload, if I overwrite, I can overwrite an existing mapping by just calling put to add a new key. Sorry, a new value for that particular mapping. And then when I retrieve it, you're going to see that it's going to be different. Okay, good. So now let's just spend the rest of the class going through a problem together, right? Because I've been claiming that maps are super useful, so I want to give you an example of a case where I can use them to solve a problem that would have been pretty gross to solve before. Again, it's sort of like recursion and iteration. Like there are, I don't want to go on a limb here and say there are problems that you can't solve without using a map, but there are times in which the solution to a problem using a map is much more elegant than the solution done in a different way. So, you know, most of the time you can skin a cat in a lot of different ways. Sorry, Ziz. But, you know, there are solutions to problems that use maps as opposed to arrays or lists that turn out to be just much more elegant and intuitive. All right, so here's my goal. Essentially what I want to be able to do is I want to be able to give, like, you're going to give me some text, like a big string. And what I want to be able to do is I want to be able to then be able to answer questions about how often a different words appear in that corpus. Now, obviously, what I could do is you could give me the string and I could just save it. And then every time you asked how many times is a particular word, I could process that. I could, you know, basically go through the string, split it into an array, and then go through the entire array looking for that word and count. But what I want to do is I want to pre-process it so that I can answer those questions automatically. Okay? So here's my starter code. I have this word counter class that we're going to work on for the rest of the class. And what it does is it has a map that it uses that it initializes in the constructor, and then you give me some an array of strings, right? This is the corpus that I'm supposed to be able to answer questions about. And then what I want is once I've created a word counter instance and you've passed me this array of strings, I want to be able to, I provide this get word count function, and that should take a word and return the number of times that word exists in the text. So right now this doesn't work, just return 0, but we're going to fix that together. Okay, so here's what we're going to do. The first thing I want to do is actually want to get out of here, go back to the API for maps, because there's a couple of, you know, just like lists, there's a couple of useful functions that we want to look at. So we've seen get and put. Get retrieves a key based on, get retrieves a value based on a key. Put adds a new mapping or overwrites an existing mapping. So it associates a value with a key. However, there's this really nice function called get or default. And what this allows us to do is to return a value from the map that basically we say if this key exists in the map, return the value for that key, otherwise return this default value. So this allows us to get around that problem where if I look up something for a key that doesn't exist, it returns null. And then let's see down here as well. There might be another, okay. Okay, so here's another potentially helpful function. This is called put if absent. And this, well, actually, no, we don't want that. Put if absent will put something only if that key. So before we saw put will always put in that new mapping. Put if absent only adds the new mapping if it doesn't exist in the map already. Okay, so let's go back to our problem here. Just keep in mind that, oh, okay, I'm getting ahead of myself. All right. So I'm going to do my work in the constructor. What I want is I want my get word count method to be very simple. It's going to use the map. But what I need to do is I need to load the answers into my map. What I want before my constructor finishes is I want this word count map to contain for each word that's in the text a mapping, a value that's the number of times that it exists within the text. So how are we going to do that? So let's walk through. And let's use our good old friend, the enhanced for loop. So I'm going through each string in the text. And now what I'm going to do is I'm going to say if word count dot get word is not equal to null, then I'm going to do word count put. Actually, here's what we'll do. Let's pull the existing mapping. So we'll say int previous current count is equal to word count dot get word. So this is the current number of times the word has already appeared. Now it's possible, now this is where we're going to do get or default. It's possible the word has never appeared before. And so if the word doesn't exist in the mapping already, that means we've never seen it. Okay? And then all we're going to do is we're going to do word count dot put word current count plus 1. Actually, we'll do it this way. Okay? And now what we're going to do down here is we're going to use this word count dot get or default word 0. And okay, so this seems to work, right? The corpus that I provided contained here twice, it contained there once, and nowhere 0 times. And again, you can imagine solving this problem in a variety of different ways, but this is a really, very elegant solution. So we wrote this quickly. Let's go through and talk about exactly what's happening here. And in particular, let's put a little bit of extra logging inside the loop that's inside our constructor. So what we're going to do is we're going to put, I'll just put a little string that prints out the current count for each word. So what you'll see is the array of words that I provided is here, here, there in that order. So the first word that I pull out is here. At that point, I've never seen the word here before. So get or default returns 0 because get or default doesn't find here in the map. So it returns this default value 0 that I've provided as part of this call to this method. The next time I see here, it had been in the map because I put it the first time. So now my loop remembers that I've seen here before and it's been in the map one time, right? So now let's see, and then, so basically we'll say, we'll just make this a little bit nicer. We'll put both the current count and the value that we're about to put in the map. So here, the first time I see here, the current count is 0, I'm about to load 1. Next time I see here, the current count is 1, I'm about to load 2. Then I see a new word there, current count is 0, I'm about to load 1. Okay. The cool thing about this is that once I'm done, this get word count is very, 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 it's very efficient. It doesn't have to do much work. I certainly don't have to go through the entire array again. So again, I mean, you could do something like this. You could say, in the past, if we were doing this together, we would have probably done something like, let's say, save text is equal to text. Sorry, save text. I've been writing too much cotton recently. Save text. So here's how we would have done this in the past. We would have said, and we can still do it this way just for fun, save text is equal to text. So I save a copy of the array, and then what I do is I say for string word in save text, if string, I need to call this something else, if saved word is equal to saved word, then counter plus plus. And then now I can just return, right? And this will still work fine. But think about it. Every time I call get word count now, I'm going through the entire text that you gave me originally. And I'm doing this repetitive work over and over again. Okay? If I go back and I use the implementation that uses a map, not only is it not that much more complicated in the sense that there's not that much more code that I have had to write, but it's a lot faster because essentially I've saved all the results before you start asking me questions. It's like you gave me this big book with all these words. In the constructor, I went through and I kept like count of exactly how many times each word, and I wrote it down on a piece of paper. And so now it's like you ask me, okay, how many times does here appears? And I look up on my list, I'm like 565, right? And I know, right, because I already did all the work. So this is, a nice example of the use of a map. And this is a data structure that, again, as you go on in your career in programming, you will find yourself using frequently. Okay, so I think that's where we're going to stop today. We will talk about how to implement a map. We'll start talking about that on Wednesday. So just as a heads up, there is some material from today's class, like some of the introductory hashing that is on Wednesday's quiz, which will take place as normally scheduled at 10 a.m. Also, so tomorrow is your first final project checkpoint. We're still working out exactly how that's going to work since you guys are remote. We may have you submit a video. We may have you get on a Zoom call with your lab staff and kind of show them what you've accomplished. But there is a deliverable for tomorrow, right? If we ask you to record a video, it'd be pretty short. We just want a really brief check-in just to make sure that you guys have done something. The description of exactly what you need to provide is up on the project write-up. And I hope you guys enjoy that. So take care of yourselves, take care of the people around you. Wednesday, as usual, 10 a.m. quiz, last quiz of the semester. As a reminder, a week from today at 10 a.m. we will have our final midterm. That will be Monday, May 4th, 10 a.m. instead of class. We will not have class that day. give you guys a little extra time to complete your final projects, which we'll start reviewing on Tuesday. And then on Wednesday, the 6th of May, we'll do our final class together. All right, that's all I got. I hope you guys are doing okay. I will see you again Wednesday at 11, and then back here at the usual time, Friday at 10.